Section 3.2, the derivative as a function. So we're going to continue that same idea that we developed in section 3.1, finding the derivative of function. Let's begin with this definition. The derivative function. The derivative of f is a function. F prime of x is equal to the limit as h is approaching 0 of f of x plus h minus f of x over h, provided the limit exists and x is in the domain of f. If f prime of x, or the derivative, exists, we say that f is differentiable at x. If f is differentiable at every point on an open interval I, we say that f is differentiable on I. Let's do this first example, find the derivative of f of x. So just as we have above, to find the derivative of x, or f prime of x, we need to apply the limit as h is approaching 0 of f of x plus h minus f of x, all divided by h. Okay, well, we can do this and approach this how I teach my college algebra students. If it seems like a lot, you can always do it in parts. You can find f of x plus h and label f of x and then input them separately so that we have f of x plus h. Well, let's find that out first. That would be, remember, for every x, we're going to plug in x plus h. So I have negative x plus h squared plus 6 times x plus h. So that we have negative times, well, we have to square this first. So that gives me x squared plus 2xh plus h squared. And then we can distribute that 6 so that we have plus 6x plus 6h. Lastly, let's distribute that negative so that I have negative x squared minus 2xh minus h squared plus 6x plus 6h. Okay, we got it. We got that first part. Okay, and second, f of x, that's just our function, negative x squared plus 6x. Okay, let's put those together to create our difference, well, our limit definition. So that I have the limit as h is approaching 0. First we have negative x squared minus 2xh minus h squared plus 6x. Ooh, I forgot that squared. 6x squared. No, 6x squared. Plus 6x plus 6h. Plus, and then we have our other function. But remember, we're subtracting, so we would have to distribute that negative. So minus negative x squared plus 6x all over h. Okay, let's go ahead and distribute that negative so that we have negative x squared minus 2xh minus h squared plus 6x plus 6h plus x squared minus 6x all over h. And things should add up to be 0. So 6x and 6x add to be 0. X squared and x squared are add to make 0. So that we're left with the limit as h is approaching 0 of negative 2xh minus h squared plus 6h all over h. Now the problem here is that I'm trying to take the limit as h is approaching 0, so I want to be able to substitute in a 0, but my denominator doesn't allow it. So I need to be able to divide out that denominator. We can do that by factoring out an h. So let's go ahead and do that. We can factor an h from our numerator so that I have h times negative 2x minus h plus 6 all over h. That gets us in our desired situation where I can divide out those h's. So then I'm left with the limit as h is approaching 0 of negative 2x minus h plus 6 all over, well, nothing, right? It's just 1. Now we can directly substitute in that value 0 for h. So that we have negative 2 times, well, that's just x, minus h is now 0, plus 6. So we have minus 2x plus 6. What did we find? We found the derivative. So we have f prime of x is equal to negative 2x plus 6. And so this equation will give you the slope of the tangent line. That's our derivative. In future classes, you might run into the delta x and delta y notations. So symbol for delta has a common meaning for change, so subtraction. This leads to an alternative definition of a derivative. It's defined as f of x plus delta x minus f of x divided by delta x, which in return equals change in y over change of x, or delta y over delta x. By letting delta x approach 0, the slope of the tangent line x and f of x is f prime of x is equal to the limit as change of x approaching 0 of f of x plus change of x minus f of x divided by change of x. And this leads us to various types of notations that you'll see for the limit. So in addition of that f prime notation, which we have seen, you can see delta dy over dx. That's really common. You'll see that a lot, especially like in Calc 3 multivariable, because we need to know what we're deriving what in terms of what. We have df dx, d over dx of f of x, dx of f of x, and y prime of x, depending on your function and your argument. So that's just notation you see. So when you see those, don't be too alarmed. It just means derivative. It means the same thing as f prime. Let's do an example. Let y equal f of x, which is equal to the square root of y. Compute dy dx. Well, what's dy dx? It's just a derivative, right? So nothing has changed from our derivative limit definition. It's just another way of writing it. There's different notations, and they all vary in our arguments, kind of what subject we're working with, how many variables, how many different variables. But so far we just have the x, right? So we have the limit as h is approaching 0 of f of x plus h minus f of x all over h. So we still apply our limit definition to this function. F of x is equal to the square root of x. Okay, let's work it out. So we have the limit as h is approaching 0 of f of x plus h. So for x, we're going to write x plus h. The square root of x plus h minus our function, which is just the square root of x, divided by h. So if you were to do this in like on a quiz or a test, right here, that's already half credit. Okay, now working it out. Well, maybe not half credit, but close to. Now from here on out, it's a matter of working it out. Now at this point, if you're in a situation where you're like, man, I'm stumped. I don't know what to do next. A helpful way to make things move in a direction you wish they would is multiplying by the conjugate. So let's multiply by the conjugate of the numerator, so that we have the limit as h is approaching 0 of the square root of x plus h minus the square root of x all over h. And we're going to multiply by the conjugate. So we have square root of x plus h plus square root of x, and the same thing in the denominator. Okay, well, I'm not going to fully multiply it out, at least for the numerator, because remember, we just have differences of squares. So since I have the same argument but with the minus and the plus, it's the same thing as something squared minus something squared, so that you're not stuck foiling and create a larger mess. So we have x plus h, square root of x plus h squared, and square root of x squared in our numerator. In our denominator, let's not multiply it out just yet. So we have h times the square root of x plus h plus square root of x. Let's go ahead and clean out our numerator so that we have the limit as h is approaching 0 of, in our numerator, that square and square root cancel out, so we're just left with x plus h, and minus that square and square root cancel out, so we're left with x. And in our denominator, we have h times the square root of x plus h plus the square root of x. Okay, so cool things happen here. We see that x minus x is 0, and we can divide out that h and that h. So what are we left with? We're left with, well, in the numerator I have nothing, so I just have that 1. In the denominator I have the square root of x plus h plus square root of x. Can then I now apply that limit of 0? Yeah, I can. If I substitute 0, it no longer creates an undefined situation for our denominator. So I have 1 divided by the square root of x plus h, which is 0, plus the square root of x. So we're left with 1 over the square root of x plus the square root of x. Square root of x are like terms, so I'm able to add them. So I have 2 square root of x. And there we have it. So what did we find? Our derivative of our function x, or f prime of x, is equal to 1 over 2 square root of x. Next question. Find the equation of the line tangent to the graph of 4, 2. So the equation of a line tangent, that phrase is the same thing as saying find your derivative. But here we have an extra part. Now we want to find the equation of the graph tangent to a particular point. Okay, so we want to find our derivative at a specific point, specifically this point 4. So if we want to use our fancy new notation, we can say dy dx when x equals 4. Okay, well, let's go ahead and work with this problem. So notice we're not really given an equation for this function, right? So what we do here is we work with that given point. Oh, I'm sorry. This is part B of part A. I was like, where's that coming from? So part A was find the derivative. Part B is work with that derivative. Well, we found that derivative. We have f prime, which is 1 over 2 square root of x. Well, we already have that derivative. Now we want to evaluate at that point 4. So what we do is we substitute in that 4. So I have 1 over 2 square root of 4. So I have 1 over 2 times 2, which is 1/4. So what is that 1/4? We use the equation that will provide a tangent line. With a point, we have the line tangent at specifically that point 4, 2. So my slope is 1/4, and that particular point given is 4, comma 2. Now, if I wish to find the equation of a line, of that tangent line, then we just use our point slope formula in a sense. So we have y minus y1 is equal to m times x minus x1. So that we have y minus 2 is equal to 1/4 x minus x1, which is 4. So our answer, once we clean it up, we're left with y equals 1/4 x plus 1. That was part B. Next example. Let gt equal 1 over t squared and compute g prime of t. Okay, so we're being asked to find the derivative. And again, we can use our derivative definition, which is the limit as h is approaching 0 of f. Well, we usually write x, but we have an argument in t. So we have f of t plus h minus f of t all over h. And if you didn't catch it, that's okay. If you still work with x, you'll still produce that same answer you're looking for. Okay, so let's go ahead and build this. So I have, for our first part, I have the limit as h is approaching 0 of 1 over, instead of t, I'm going to write t plus h. So I have t plus h squared minus our function, which is 1 over t squared all over h. Okay, well, this is a complex fraction, right? So if you ever are in doubt, remember this just means a division sign. And how do you divide fractions? You change it to multiplication, and you flip your second. So if you like to, you can think of this as 1 over t plus h squared minus 1 over t squared times 1 over h. Remember, you keep your first fraction, you change it to multiplication, and here we have h over 1, right? And then you flip it. Keep, change, flip. That's what I always tell my students. Okay, so we have this other way of writing it, which kind of makes more sense to our eyes. Okay, so what is our next step? We want to go ahead and create, combine like terms. So you want to create a like denominator. So you're going to multiply this side by a t squared and a t squared, and this side by a t plus h squared, top and bottom. So that we're left with the limit as h is approaching 0 of t squared minus t plus h squared all over t squared times t plus h squared times 1 over h. Okay, let's work out our numerator and see what happens. Let's multiply that out. All right, so we're left with t squared minus, we have t squared plus 2th plus h squared all over t squared times t plus h squared. And I can write the h in the bottom if you want. Multiply it in. Okay, let's clean up our numerator still so that we have t squared minus t squared plus 2th plus h squared all over t squared times t plus h squared times h. Well, we see some cool stuff happening. My t squares add to make 0, so that we're left with h squared plus 2th. I don't want to confuse my t's and my pluses. All right, so we have finally managed to cancel this h, and we'll do that in the next step. So I have t squared times t plus h squared times h. Now our problem here is that we're trying to apply this limit as h approaching 0, but we have the h in the denominator. Well, we see that if we factor in h, I'll be able to cancel that h. So that if I factor in h, I'm left with h plus 2t. And the bottom I have h t squared times t plus h squared. My h's are now gone. So now I can go ahead and apply the limit. So I have the limit as h is approaching 0 of h plus 2t over t squared times t plus h squared. Okay, now I can go ahead and directly substitute that 0. So I have 0 plus 2t is just 2t. T squared plus, well, my h is 0, so I have t squared. T squared times t squared is t to the 4th. And I didn't expand correctly. So I was supposed to distribute that negative to each one. So all of these are negatives. Negative, 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 and thus this is negative. And that is our answer. So we found the derivative, g prime of t. Okay, now let's take a look at our function as a graph and work with the derivative that way. So in this next example, sketch the graph of f prime from the graph given of f below. Hint, determine the points where the rate of change is 0. Okay, so we have to consider some things about our graph. To begin, I have to look at where my graph is going to be 0 and how that applies. Okay, so to begin, what is f prime? It's a derivative, right? And what is the definition of a derivative? It's the slope of our tangent line. Okay, well, if I have a point and I create any random point on the line, say this point right here, well, I already have a line tangent to it. So I just need to find that particular slope. So if I look at this part, just this part alone, what is the slope? Well, remember your slope is your rise over run. So your rise over your run. What is our rise and run? 1 and 1, right? Towards a negative direction. So here our slope is negative 1. Pretty cool, right? Now what's going on right here? Just pick a point on the line. Well, remember your slope is your rise over run. So here we're going up 1 over 1 to find our next point. So we go up 1 over 1. Our slope is positive 1. Now let's consider what's going on for the rest of our function. You can pick any point you like on your graph. So if I pick a point here, what's going on? I rise down and I run 2. So you have a rise and a run. You have a slope of negative 1/2. So we have slopes according to each part at these straight lines. So if we wish to graph or talk about the derivative, these derivatives are found here. So let me draw another graph. and let's graph these graphs. So that first one has a slope of 1. So of -1. So I will look here at -1, and this is only from this part, from this -2 to this -5. So from -2, 3, 4 to -5, I will be at -1. So I draw open circle all the way to 5. That's an open circle. Okay, next I have a slope at 1. Now the slope of 1 ranges from -2, and then it stops at 0. So from -2 to 0, I will be at that 1 mark. And lastly, I have a slope of -1/2, starting at 0 and continuing on until it looks like it stops at 5, right? So from 0 to 5, that is my slope at -1/2. So from here to 5. And there we have it. Our derivative is our slope. And if I found the slope, if I directly have the slope, then I can apply it this way. What if your graph is not a set of straight lines with a rise and a run? What if you have a curve? That leads us to our next example. Sketch the graph of G prime using the graph of G. Okay, so again, your derivative is your slope at a tangent line. So let's start by setting out where your slope is 0. Well, you have the line y equals 0 at those peaks. So we have these peaks here. This peak kind of looks like it's at 1, right? This peak here, and this peak here. That's where our line is equal to 0. So we have these values where these values x equals -3, -1, and 1, where you have a slope that is 0. It's a horizontal line. If that's the case, if your slope is 0, then your derivative, g prime of -3, g prime of 1, and g prime of -1 are going to equal 0. So if we were to graph this, think of your college algebra experience. This is your zeros, which are also your x-intercepts. So if we're graphing our derivative, we have zeros at -3, we have zeros at -1, and at 1. These are zeros of our derivatives. This is our derivative graph. Okay, now let's consider what's going on besides that. So we also have these positive values where our slope of our tangent line is positive. So if I pick a point on this part here, I see that my slope is positive, and same thing for right here. My slope is positive, it's going up. I'm not too sure what it is, but I know it's going up, it's positive. So at these positive slopes, how does that translate to our derivative function? Well, what this does is it just tells us that our derivative is positive, therefore above the x-axis. And where does this happen? This happens from, well, it seems like it continues on to -infinity, and it stops at -3. So when x is less than -3, and it happens between -1 and 1. So at those values, my graph will be above the x-axis. So from negative infinity to 3, it's going to be above the x-axis. And between negative 1 and 1, it's going to be above the x-axis. So I'm not sure what's happening, but I know it's above. So we're blindly graphing. Now, what's happening from there on out? So we see that between negative 3 and negative 1, if I draw a point and create a tangent line, we have a negative slope. Same thing here. From positive 1 and on, we also have a negative slope. So when we have a negative slope, then our G prime graph is below your x-axis. So this is your x-axis, it's going to graph below. So we're going to be below here and below there too. And we have this as our graph for our derivative. Does it remind you of graphing polynomials? Because that's what I was thinking about the whole time. One last problem in the theorem. The theorem differentiable applies continuous. So continuous means it doesn't stop, it goes on forever. Well, not forever, but you don't pick up your pencil. And it's a smooth, continuous line. If f is differentiable at a, then f is continuous at a. When f is a function not differentiable at a point, a function is not differentiable at a if at least one of the following conditions holds. F is not continuous, meaning there's a break. F has a corner, like a cusp, some sharp point. And f has a vertical tangent at a. So these are parts where it's not differentiable. So I leave you with this problem. We're trying to determine if it's continuous, yes or no, and why. So we see that our questions ask, consider your graph, and we have this graph G. First, we want to see A. Find the values of x on the interval from negative 4 to 4, so this whole picture, at which G is not continuous. So based on our continuity, we have issues at these values here because there's a gap, and here because there's like a cusp, right? There's a sharp point. For B, find the values of x on the interval from negative 4 to 4 at which G is not differentiable. All right, so by our theorem above, not continuous can be determined to be not differentiable. So we would say that it's not differentiable at these points. And B, sketch the graph of its derivative. Let's go ahead and sketch the graph of the derivative quickly. So let me draw kind of a mirror of it. So I'm not sure what the slope is, and neither are we because they didn't give us this information. But I know this slope is positive. So we have this positive slope from negative 2 to 4. So 1, 2, 3, 4, 1, 2, 3, 4. So from negative 2 and on, I have some positive slope. And then from negative 2 with the open circle to 0, we have a negative slope. So when we have a negative slope and it's not a straight line, we determine that's going to be, I wrote positive, it's going to be below our x-axis. So from negative 2 and on, It will be below our x-axis. And then we see that from 0 to that stopping point of 2, we have a positive slope. So it's going to be above our x-axis. So I'm not sure what's happening, but I know from from 2, it's going to be above. And then from there again, from 2 to 4, it's going to be below. And there we have our derivative. Now I should have started by pointing out these points. So we have that slope of 0, so that translates as a point along our derivative. Here I have a point at 0, so that translates as a point along our x-axis. That should have been a better starting point than just jumping into slopes. Alright, I hope you enjoyed this function. Derivatives are the funnest for this course. I enjoy them. I hope you enjoy them as well. We'll learn some new tricks on derivatives, and we'll move on past this like difference quotient rule for a derivative. All right, that's it for this section. Thank you.